All right, this is nothing new. We just got to dig deep. All right, we have done this in the past. So my first question from you is take a look at what I'm asking you to prove. We have seen this in a previous unit before. I need your help. What unit did that come from? When I multiply two segments together, it's equal to another two segments multiplied together. You have seen this in a previous unit. We just got to dig deep together here and try to remember what unit it came from, because then we'll start building from there. Even if it's a guess, it's a guess. What unit did we do these types of proofs in? Even if you remember a part of the reason, maybe you would write for that statement. Looking for anything, because I don't want to give it away. Well, okay, maybe I'll give you, yes, Romeo?
Product of the means is equal to the product of the extremes.
That would be the reason for this. If I put that in my statements, which I will at the end, product of the means equals product of the extremes. We're moving. That's a big step forward. What unit was that from? Means and extremes are equal. Because you couldn't write that down unless you knew what about the triangles? Similar. There we go. We found it. So this is going to turn up being a similar triangles proof. And we should know this. What's the only way in a proof anyway? We prove two triangles similar. Angle, angle. All right, let's go. So the first thing I need your help with is angle, angle in these two triangles. Get two pairs of angles congruent for me, so I can get to this means and extremes part eventually. Name one pair of, I'll start with somebody here. Name an easy pair, right? It's staring you right in the face, the one pair. So name a pair for me that you definitely know are congruent here. One, George, hello.
AED.
Yep.
CD.
Yep, they're what type of angles?
Vertical.
Good. So AED congruent to CEB. Vertical angles congruent. Good start. So I need another pair. And this is going to come from a circle fact. All right. This is going to come from a circle fact. And I'll even write them down. You just got to give me the reason. We could go C and A congruent, or we could put B and D. You pick. All right. C is congruent to A, and B is congruent to D. It's just a matter of which pair you want. So angle C is congruent to angle A. I just need to know the why from you guys. Why C and A and B and D are congruent. And this is a circle fact. Why C and A are congruent. All right, let me start you off here with somebody. You don't need to tell me. I'll get it from you, though. 11. What type of angles are C and A?
They're both.
It's been a couple days, but
have, yeah.
C and A are on the circle. Both sides are chords. Those are called. I'll spot you the eye.
Inscribed.
They're inscribed, right? And they're both inscribed angles. Which arc are they both drawn to?
Arc B.
B. Everyone see they're both drawn to the same arc. So inscribed angles drawn to the same arc are congruent. So there's your angle, angle. So now next step, after we get that reason down, they're similar. So your triangles are similar now. So name them. Triangle CBE. Similar to ADE. Everyone check your statements. Did you write the similar sign or the congruent one? Make sure you wrote similar, not congruent. By angle, angle. Ooh, yikes. We're going to have you dig deeper now. The next step is not means equals to extremes. I got an in-between step before I say means and extremes are equal. That'll be step 6. Step 6 will be the proof statement, means equals the extremes. We got an in-between step that gets me from similar triangles to means and extremes. Think you got it, Zach?
Yeah. You have to do AE is equivalent to CE, and BE is equivalent to DE, or is it similar?
No, I don't want the sides equal. How?
Proportion.
Yeah, remember, if the triangles are similar, sides are in proportion. I think that's probably what you're starting to think about, but I got to put them in a proportion. All right. What proportion? Well, AE is in my proof statement, right? And eventually we're going to have to multiply that with BE. So where in my proportion does BE have to go? Only one spot. I can put BE. If I'm going to multiply it with AE, where's BE have to go right now in my proportion? If it's going to get multiplied by AE. 18, where does BE have to go? It's got to be multiplied with it. If I put BE right underneath, Adrian, there's no way those two are going to get multiplied.
Across from it and under it.
Good. It's got to go diagonal because remember, how do you solve these? Cross multiply, right? So it's got to go there. And then the other two sides have to go in the other two spots, CE and DE. Ooh, why is that true? Romeo, go ahead.
Corresponding sides are in proportion.
We had a little shorthand for that, I believe. Corresponding sides and similar triangles are proportional. Anybody remember the shorthand? It was the cousin of CPCTC. CSSTP. Yep. Corresponding sides, similar triangles are proportional. Now you can cross multiply and say the means and extremes are equal. AE times BE equals CE times DE. This is product of the means equals product of the extremes. So yes, I wanted to review with you, but also this leads into today's circle fact of the day. So here's what you guys just proved for me. Here's what you just proved. 8. What is CD in the circle? CD is, what do we call that in the circle? A chord. And what's AB? Everyone see those two chords? They're intersecting, aren't they? So here's what we just found out. In a circle, if two chords intersect, which I have, you have two chords in that diagram that intersect. Ready? The product, that's the answer when you do what? Okay, so the product of their segments are equal. And I'll show you what I mean on the diagram in a second. The product of their segments are equal. That's what you guys just showed by doing that means and extremes proof. Whoa, 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 whoa. Don't go on. Just say on the diagram for me. I want to show you exactly what I mean and how we're going to use it. Everyone good? I'll go to the dot. Here's what I mean. Get rid of. You don't have to put this on yours. I just want to show you exactly what I'm talking about. That's 2. That's 9. What's the product?
11. Sorry, 18.
18. Everyone agree? That's going to be the same product for CE and ED. Everyone see how this theorem works? Segment times segment on one chord equals segment times segment on the other chord. That's what this theorem is today. All good. All right, let's try it out now, but with x's in there now, with variables. All right, everyone see two chords. They're intersecting. So I know the product of their segments are equal. So I'm going to take somebody here first, one chord only. Tell me the two segments on one of the chord. 6. One chord is broken up into what segments? 8 times the other segment, 2.5 on one chord. Now go to chord number 2. Tell me the two segments created on the next chord. 5. X times 2. That's how this new theorem works. And this is about as easy as it gets. Right here. So we got x equals, let's see if I do that twice, 20. 2x equals 20. 10, how's that looking? 10? Like I said, about as easy as it gets. Now it's going to get a little tougher now. Number 2, do you guys see two chords that intersect on the diagram? Do you see two chords? I'm going to highlight them on mine. Here's chord number 1, the 8 and the 10. And what's another chord you see? Sometimes we call it the what? Diameter, yeah. So there are the two chords that intersect. And everyone see the 12? What's the 12? Radius. We may need that, but not for this fact here. All right, so let's start with my pink chord up there. My pink chord is broken up into what two segments? 17? 8 and 10. So 8 times 10. Everyone's with me so far. Now what about my yellow chord, aka the diameter? What's that broken up into? Well, can you at least tell me what one segment is? It's already labeled. What's one segment? What is it? That's the radius, though. One here is what? One segment is x. Now here's the hard part. How do you write the other segment? I know one segment's x. Let me do it in blue. I'm talking here to here. There's the other segment. How do I figure out how long that one is? Because I got to multiply that with x. How long is that segment? Well, let's do it this way. How long is the whole diameter? Good, 24, right? Because you know the radius is 12. Whole thing's 24. That's already x, right? Whole thing's 24. This part's x. So what's the other part? 24. All right, we got it. Boom. You're not going to like how to solve it either, but at least we're on the right track. So x is one segment, 24 minus x the other segment. All right, you ready? Not going to like this, but oh well, that's why you're in this above average class. 80 equals 24x minus... Oh, we've been here before. This isn't the first time we've done these. Next move. I do not like this at all. Negative. If it was positive, I'd be okay. I'm good. I don't like it. Negative. So how can I make it positive? Oh. I guess I could do that. Move everything. I got to get one side equal to what here? 0. You're about to factor, everybody. I see a squared. I'm about to factor. And I can't factor unless one side's equal to 0, and I prefer my x squared to be positive at all times. So let's move everything over to the left. X squared. What else is here with me? Minus 24x. 80 still stays positive. Uh-oh, here you go. Not our favorite. Two numbers. What are you thinking about? Two numbers or putting in your calculator? Two numbers that do what? What do your two magic numbers do here? Multiply to 80, but add to 24. All right, let's go. Find them. Two numbers, multiply to 80, multiply to negative, or add to negative 24. You got it. 10 and 8, those are the ones that first come to my mind, but that's not going to work. Can't get 24 from there. Come on, dig deep. Don't quit. You got it. You got it. You got them. Oh, 16 numbers.
Right. X minus 20 and minus 4.
Minus 20, minus 4. Good. They multiply to 80, but add to negative 24. Good, good. And now you got to tell me what x equals. Set each of them equal to 0. Let me know what x equals. We still got to talk. Uh, 14, two values of x.
20 and 4.
Yep. Usually when we get a negative number, that kind of alerts us to maybe we got to get rid of it. Anybody got a problem with any of those positive answers? I do. 20 and 4, I got an answer that doesn't make much sense. Go back to your diagram. What's the radius length again? So how can x be 20 and be bigger than my radius? Right, and that's definitely smaller than the radius, part x, right? So there's no way my answer can be 20. Got to be 4. Can't have an answer bigger than the radius. All right. Whew. Need a breather now? No joke. All right, we got another one here. Come on. You got it. Chord CD. Find the length of the chord. Ooh. If it's 3 centimeters from the center. Can you put a 3 somewhere for me? Chord CD is 3 centimeters from the center. And yes, you can assume that black dot is the center. So hopefully we're throwing a 3 spot right here, 3 centimeters from the center. Radius of 5. Can you throw the 5 on there anywhere? Right from the center to B. And now, hey, now that we know this radius is 5, are you putting on a new number on your diagram too? Everybody putting another number that's not even listed? How about from the right angle to A? 2, yeah. Radius is 5. If that's 3, I got 2 more units to go. All right, I see you. Do you see 2 chords that intersect? I see chord CD intersecting with chord diameter AB. All right, let's start with the diameter, or the yellow chord. What are the 2 segments on the yellow chord? Don't get fooled here. What are the 2 segments that the yellow chord is broken up into? Yes, Emma?
2 and 8.
2 and 3 plus 5. We okay? We sure there before I move on? Part segment number 1, 2. Segment number 2, 3 and 5. Now, they didn't give me squat about chord CD. They didn't give me anything about it, did they? Like, it's got to be this part times this part, but I don't even know what they are. Do we know something about them from this unit? Theorem. Theorem. Why?
Because chord that's goes through the diameter, goes through and makes a right angle bisects it.
Everyone remember? Diameter perpendicular to a chord bisects the chord. I don't need to know it. What can I call both pieces? Yeah, they're both the same. There you go. That's why this unit's so darn tough and tricky. Had to remember that theorem to do a new fact. And now it's pretty easy, right? 16 equals x squared. X equals 4. Problem though, read the question, right? Not going to accept 4. We're looking for the length of the chord. So how long is CD then? 4? 8. All right. Questions? Draw yourself a diagram for the next problem. Draw yourself a diagram. None is given, so we got to do our own here. Not that. AE, you guys threw on what, 6-3? EB 16. What are you guys doing here? RE to ES, 3 to 4. Putting X's with them. Good. Putting X's. So RE, hopefully we have a 3X on there. ES, hopefully we have a 4X. So I have two chords that intersect. 3 times 16. There's one chord broken up. And the other chord, 3X and 4X. How's the algebra on this one? What's your deal here? 3X times, not 7X, not even 12X. What do you got for me here? It's not 7X, we're not adding. It's not 12X, because you're forgetting something. 12X squared. Ooh, we okay? 12X squared. X times X is X squared. Now what's your next move? Yep, go ahead, get the 12 out of there. X squared equals 4. X equals 2. Go ahead and do part A and B now. How long's RE? 16. How long's RE? 6. And then part B, how long's ES? 19? 8. Got it. All right, any issues with this? Because I'm going to go over one last theorem here with you. I had to figure out where to put this in the unit, and this was the best, since we're talking about chords today, this is the best day to do it. Any issues with the segment times segment? All right, this one's not bad at all. Here's, in a nutshell, here's what it's saying. Hey, I have two chords, they're parallel to each other. Two chords, they're parallel. So in this case, AB parallel to CD. I have two chords that are parallel. If that is true, that implies the arcs in between are congruent. Two chords are parallel. The arcs in between them are congruent. All right. Two chords are parallel. The arcs in between are congruent. All good? All right, I'll do number 1 with you. Then you can do number 2 and 3 by yourself or with people around you. AB parallel to CD. Got it. Name two arcs that are congruent now. 5, based on what we just talked about here. CD parallel to AB, which two arcs are congruent? What are the arcs in between those parallel lines? Arcs. So here, yep, and BD, CA. They're congruent to each other. They have the same measure. I gave you arc A, B is 80. What about arc CA? All right, well, one thing you got to notice in this problem. 3, what's COD here in this diagram? Diameter. So it cuts it off into 180 degrees on each end, each side, right? So I have 180 degrees down here. So measure of CA, I'll do 180 minus 80. And then what do I know about what's left over? They're equal, so I can divide it by 2. Because CA and DB are equal. So you're looking at 50 here. 100 divided by 2. All right, try out the next 2 when you're ready on your own or with people around you. It's up to you. Chords are congruent, so are the arcs. Remember, congruent chords imply congruent arcs.